Hello! In this video, I will demonstrate how to use the automatic design tool Veltronics Accelerate. Previously, I gave an overview on the benefits of hardware acceleration and Accelerate's key features. The example software task shown is 3 global variables and an add operation. Accelerate supports a subset of normal C code. The calculations in the function void calc void, in this case just the add operation, will be accelerated. Global variables A, B and C will each be allocated an address in the accelerator's memory. I'll switch to the Accelerate GUI and start a new project with that C code added to the project. The example code is in the file add.c with the following contents. I'll add this C into the new Accelerate project. Next, Accelerate needs to be configured. In this example, I will set the target to be the Altera ARIA 5. I'll make the accelerator have separate clock domains for its underlying submodules and have it controlled with a control bus rather than through dedicated start complete ports. Also, I'll give the accelerator a name and add a memory access slave to the accelerator. Configuration is done by bringing up project options under the project menu. I'm leaving the Generate Test Bench and Generate Fast Model options off. These objects can be used to test the generated accelerator. Any C compiler flags that you wish to use can be specified in the Extra Flags field. For example, if your code contains macros normally defined using #define, you can use the -d flag to define them. I'll give the accelerator the name add. The last option enables or disables the memory bus. After saving the project, the configuration file is created. Now that the options are configured, I'll run Accelerate. It should take only a few seconds to generate an accelerator. As you can see in the console log, Accelerate has finished running successfully, indicated by an exit code of 0. At the end of execution, an accelerator in the form of RTL Verilog is obtained. The interface of the accelerator corresponds to how Accelerate has been configured. The generated accelerator has separate clock reset pairs for the following submodules of the accelerator: the input-output interface, shown in blue, the calculation logic shown in orange, and the memory interface shown in green. The interface IO_CTRL to the input-output submodule is the control bus that is used to trigger the accelerator's start of execution or monitor the accelerator's completion. The interface MEM to the memory submodule is the memory bus, which is used to read and write the accelerator's memory, for example when accessing global variables A, B and C. I'll now show the output of Accelerate's execution. Listed here are the original C code add.c, the configuration file, and accelerate's output. Add.v is the generated RTL Verilog. This Verilog describes the interface, the three submodules, and the calculations. A tool like Altera's QSys can be used to connect this accelerator to other systems without having to worry about the details of the interface. The Verilog is accompanied by add_hw.tcl. This is a Tcl script that describes the accelerator module to facilitate system integration through QSys. The MIF file describes the initial state of the accelerator's memory submodule. Global variable initializations in the C code will be reflected in this memory initialization file. The memory access header file provides helper functions for accessing global variables in the accelerator's memory. You can include this header file in order to use these functions in software code that should control the accelerator. The RPT files are report files that can contain information such as hardware target resource use, total number of clock cycles required, and the scheduling of operations. This ends my explanation of how to use Accelerate to generate a hardware accelerator from a software task. Please feel free to contact us if you have any questions about Accelerate or anything related. Thank you for listening.